Hello and welcome to this GeoStudio webinar on simulating rapid drawdown in SeepW and SlopeW. I'm Catherine Dompierre and I work as a research and development engineer at GeoSlope. A recording of the webinar will be sent out so participants can work through the project on their own at a later date. Participants will be muted during the webinar, so please use the chat feature to enter any questions you have. I will respond to questions as quickly as possible. For those of you that are relatively new to GeoStudio, it is a software package developed for geotechnical engineers and earth scientists, comprised of several products. The range of products allow users to solve a wide array of problems that may be encountered in these fields. In today's webinar, we will use two of the GeoStudio products, SeepW to consider groundwater flow and SlopeW to determine the associated stability of the system, given the computed pore water pressures. Those looking to learn more about our products, including background theory, available features, and typical modeling scenarios, can find an extensive library of resources on the GeoSlope website. Here you can find tutorial videos, examples with detailed explanations, and the engineering books for each product. This webinar will consider pore water pressures and the associated stability of an embankment dam during and after reservoir drawdown. A steady-state SeepW analysis sets up the initial conditions in the embankment, given full reservoir conditions. Two drawdown scenarios are simulated with transient SeepW analyses. The first scenario considers instantaneous drawdown, while the second considers reservoir drawdown over a given period of time. The stability of both scenarios is determined in SlopeW, given the simulated pore water pressures. We will now review the problem details by going through a typical modeling methodology, which we will follow in this webinar. The first step is the idealization of the physical system. In GeoStudio, this involves creating the project geometry, for example, all lines, points, and regions that define the model space. In this case, we have an embankment dam made up of a single region. A tow drain is present at the downstream portion of the dam foundation, and a point defining the maximum reservoir level has been added to the upstream face of the dam. The second step is to select the appropriate physics. In GeoStudio, this involves two sub-steps, the first of which is to select the desired analysis type. For example, in SeepW, do we want to simulate steady state or transient conditions? The second sub-step is to define our material properties. In this problem, the embankment dam is comprised of a silty clay material. Because we expect there to be both saturated and unsaturated conditions within the dam, we will use the saturated-unsaturated material model for the SeepW analyses. This material model requires functions for volumetric water content over pore water pressure, here on the left, and the hydraulic conductivity over pore water pressure on the right, or over suction as shown here. These functions can be estimated in GeoStudio using the provided estimation routines for typical soil classifications. For the SlopeW analyses, we will use the Moore-Coulomb material model with the given properties for unit weight, cohesion, and the friction angle. The third step in a SeepW analysis is to define the boundary conditions. For the instantaneous drawdown case, the reservoir level drops to 0 meters at the beginning of the transient analysis. Thus, a seepage face is placed on the upstream face of the dam where the reservoir had previously been applied. In the second case, the reservoir level gradually decreases over 5 days. This requires the application of a boundary function along the upstream face of the dam, as shown here. In a SlopeW analysis, the third step is to define our slip surfaces. The stability analyses in this project will have the same slip surface definition from right to left using the entry and exit method. The fourth step is to solve the analysis, followed by interpreting the simulated results. This final step is the most important component of the modeling methodology. In SeepW, we can visualize the results by adding contours to the domain, like the total head contours shown here. We can also add isolines to represent the phreatic surface at one or all time steps. The draw graph dialog offers many options for plotting and interrogating the simulated results. For example, the SlopeW results for factor of safety, over time are illustrated here. We will now switch to GeoStudio to go through the rapid drawdown example. In GeoStudio, you will notice there is a region representing a simple embankment dam cross-section. There are two additional points present. The first represents the reservoir water level before drawdown, and the second represents the horizontal extent of the tow drain. Thus, the basic geometry has been created for us. First, we will set up the analyses that represent the rapid drawdown case in the project file. To do so, open the Define Project dialog by clicking on the Define Project button. This is where we define the geometries and analyses present in our GeoStudio file. There is already a steady-state seepage analysis associated with the dam cross-section geometry. This steady-state analysis will provide the initial conditions for the drawdown analyses given the reservoir at the maximum level. Under the Physics tab, you will notice a list of the possible physical processes that can be included in our analysis. When a SeepW analysis is created, the water transfer option is automatically selected. This is the only physical process we wish to consider in this example. I will now add a transient analysis to the project by clicking on the Add button, going to SeepW, and selecting Transient. A new analysis appears below our initial conditions analysis as its child. We can rename the analysis to 1A Rapid Drawdown. Under the Water tab, we see that this new analysis will obtain its initial conditions from the parent analysis. A transient seepage analysis simulates changing pore water pressures over time. Consequently, we need to define the time steps for this analysis under the Time tab. The analysis will run for a duration of 30 days. There will be 10 time steps. And in this case, we are going to select the exponential option with an initial increment of 0.25 days. The exponential time-stepping option is ideal for problems with substantial pore water pressure changes at the beginning of the analysis that gradually decrease over time. In this problem, we wish to consider the stability of the dam given changing pore water pressures following drawdown. So we want to add a slope stability analysis associated with our rapid drawdown analysis. To do so, I will press the Add button, go to Slope W, and select Limit Equilibrium. You will see that the slope stability analysis appears under our rapid drawdown analysis. That was because we had selected the rapid drawdown analysis when creating this new slope stability analysis. I will rename the slope stability analysis 1B slope stability to differentiate it from the other case that we will also create in our project file. Under the Settings tab, you can see that the pore water pressure conditions are being used from the parent analysis. In this case, the time step that it's using the pore water pressure conditions from is selected to be just the last time. However, we want to determine the stability at each time step in our transient seepage analysis. To do so, make sure that all is selected under the Time dropdown. Now go to the Slip Surface tab. We want to make sure that the direction of movement is from right to left. We have now finished setting up the analyses associated with the first rapid drawdown case, so I will close the Define Project dialog. To complete the second step, defining our physics, we must now enter the material properties. Let's first define the hydraulic properties by selecting one of the seepage analyses and going to Define Materials. This opens the Define Materials window. There are currently no materials listed here, so we will create one from scratch by pressing the Add button. I will rename this new material Embankment Fill. As previously mentioned, we expect there to be both saturated and unsaturated conditions present in our dam, so I will select the Saturated-Unsaturated Material model. The first function that must be defined for this material model is the volumetric water content function, representing water content over pore water pressure. To create this function, press the ellipses button beside the drop-down menu and add a new function. I will call this function VWC function for volumetric water content. Under the type drop-down, we will select volumetric water content data point function. I can now press the estimate button that appears in this window to use the sample function's estimation method to generate the function based on the soil type. This method requires the saturated water content, which I will enter as 0.7, and the sample material, which we will select to be silt. For easier visualization of this function, press the Xlog option at the bottom of the function window. To finish defining the volumetric water content function, we must also add a value for the compressibility of the soil, which defines how the volumetric water content of a saturated soil changes with pore water pressure. I will enter a value of 0.0001 per kPa. After closing the defined volumetric water content functions window, we must now select the function from the drop-down menu. We will now define the hydraulic conductivity function using a similar method. First, click the ellipses button, add a new function, which we will rename K function. Select the hydraulic conductivity data point function type from the drop-down menu, and again press the estimate button. In this case, I will use the Van Gunsten estimation method and the volumetric water content function we just defined to estimate the hydraulic conductivity function. We must also enter the saturated hydraulic conductivity. Let's enter 0.864 meters per day. Finally, we need to enter the residual volumetric water content. I will enter a value of 0.1 and then press OK. Logging both the X and Y axes provides the best visualization of the function. After closing this window, I will select the K function from our drop-down menu. We are now finished defining our hydraulic properties for the embankment fill. We want to define our slope stability properties now. To do so, click on the Slope W analysis. You do not have to close the material definition window to do so. Select the Moore-Coulomb material model from the drop-down menu. I will enter a unit weight of 20 kilonewtons per meter, a cohesion of 5 kPa, and a friction angle of 27 degrees. There are many different options that may be defined under the tabs in our materials definition. In this case, we will define our materials just using the basic properties. We can now close the material definition window. We now want to apply this material to the domain for all analyses in the project file. Click on the Draw Materials icon at the top of your window. Select the Apply to Multiple Analyses option and check all of the analyses. Then hover your mouse over the dam domain. You will notice that the mouse changes from white to black, and a square appears at the end of the arrow. You can now click in the domain to apply the material to all 3 analyses. We see that the status in the Draw Materials window shows us that we have successfully assigned our embankment fill to this region. The next step is to define our boundary conditions in our seepage analyses. In the initial conditions analysis, you will notice that the boundary conditions have already been applied to the domain. Go to the Define Boundary Conditions window in order to see what boundary conditions each represents. The purple boundary condition applied to the upstream face of the dam is called the steady-state reservoir boundary condition. This represents the reservoir at the full level of 8 meters. The red boundary condition that represents the tow drain is a water total head boundary condition of 0 meters. In this case, the tow drain has a pore water pressure or pressure head equal to 0. Because the tow drain is at an elevation of 0 meters, this means that the total head is also 0. In this case, because the elevation is 0, we could either specify a water total head of 0 or a water pressure head of 0 meters. You'll notice that there's also a seepage phase boundary condition present in our Define Boundary Conditions window. This boundary condition can be applied to nodes where we believe seepage may be occurring. The GeoStudio solver will then determine which of these nodes are associated with water leaving the domain, and which of the other nodes have a pore water pressure that's less than 0 or negative. Our boundary conditions are complete for our initial conditions analysis. Let us now go to the second seepage analysis, 1A rapid drawdown. You will notice that the same boundary conditions have been applied in this analysis. However, we need to change the boundary condition applied to the upstream face of our dam to represent instantaneous drawdown. In this case, the upstream face of the dam would become a seepage face. We therefore do not need to define another boundary condition at this time, because we can use the existing seepage face boundary condition. After closing this window, I will click on the Draw Boundary Conditions option. I'll select the seepage face boundary condition from the drop-down menu and then hover my mouse over this upstream face of the dam. You will notice that a line appears at the tip of the arrow. This indicates that the boundary condition will be applied to a line. Click on the line and you'll see that the boundary is applied to this face. We are now finished defining our boundary conditions for our seepage analyses, so we can close this window. In a slope W analysis, we do not apply boundary conditions, but rather define our slip surfaces. In the stability analysis, click on the Draw Entry and Exit Slip Surface icon, or go to Draw, Slip Surface, Entry and Exit. We can manually enter the points into this dialog to define our entry and exit ranges, or we can draw the ranges directly on the domain. I will draw the exit range from 0 meters to 4 meters elevation on the upstream face of the dam. The entry range will simply be the crest of the dam. We can now close this window. To review, we have now completed setting up the model geometry, establishing the appropriate physics, including defining our material properties, defining and applying our boundary conditions, and defining the slip surfaces. We have done so for the first case that considers rapid drawdown. Now we need to add the second case representing gradual reservoir drawdown. To do so, I will go back to the Define Project dialog. The easiest way to define the analyses associated with Case 2 is to clone the analyses associated with Case 1. To do so, click on the analysis 1A Rapid Drawdown, select the Add button, go to Clone, and select Clone Analysis Branch. When you do so, you see that 2 analyses are added to our project file that replicate the transient seepage analysis and associated slope stability analysis. I will rename these analyses 2A Gradual Drawdown and 2B Slope Stability. Because we cloned the existing analyses, the time stepping, materials, boundary conditions, and slip surface definition are all the same in these new analyses. The only thing we have to change is the boundary condition representing the reservoir in the gradual drawdown seepage analysis. Go to the analysis 2A Gradual Drawdown, select the Draw Boundary Conditions icon, click the Define button, and we see that the Define Boundary Conditions window opens. We now want to add a new boundary condition to represent reservoir drawdown over time. I will add a new hydraulic boundary condition, change its name to Reservoir Drawdown over time, and select the kind Water Total Head from the drop-down menu. For this second case, we want to set up the boundary condition with the total head decreasing over time. Therefore, we need to select the Function option. Here we will add a new function by pressing the ellipses button. Add the new function, give it a name, gradual drawdown, and select the spline data point function from the type drop-down menu. We can now add data points using the entry boxes that appear. I will add 2 data points. The first one is at a time of 0 days when the reservoir is full at 8 meters. The second point represents the drawdown after 5 days when there is no water left in the reservoir. You will see that a linear function appears from 8 meters to 0 meters over the 5 days. After 5 days, the solver assumes that the water level is at 0 meters for the remainder of the analysis. After closing this window, I will select the new function in the drop-down menu. Now we must select the potential seepage phase review option at the bottom of the window. This means that the solver will determine which nodes above the water level have water seeping from them as the reservoir level goes down. Finally, I will change the boundary condition color to differentiate it from the tow drain. After closing the boundary condition definition window, I will assign this new boundary condition to the upstream face of the dam. I do not need to change anything in the slope stability analysis for case 2, as we wish to consider the same slip surfaces as in the case 1 stability analysis. I'm now ready to solve our analyses, so I will press the Start button in the Solve Manager window. Once our analysis finishes solving, I will look through the results from our seepage analyses. Click on the Initial Conditions analysis. To view seepage results, we can add contours to the domain by going to the Draw Contours dialog using this icon at the top toolbar. Here we have a total head contour that already exists. We can also add contours of a wide range of other parameters. I will add a new contour for hydraulic conductivity. Under the category, select Material Properties and Water X Conductivity. We can also add a legend by clicking the Show Legend option in this window. Back in our GeoStudio window, we can select the viewed contours from the drop-down menu. You will also notice the vectors are present on the domain, indicating the direction and magnitude of water transfer. Finally, a blue dashed line represents the phreatic surface or the ISO line for a pore water pressure of 0 kPa. In a transient seepage analysis, for example, if we go to 1A rapid drawdown, you will notice that we can manually move through the time steps by clicking on the first step in the Results Times window and using the downward arrow button to move through the following steps. You will notice that the ISO lines for all steps are visible on the domain for the first case. If we go to the second gradual drawdown analysis, these ISO lines are also present on the domain. As we move through the time steps, you will notice that the bolded line represents the phreatic surface at that time step. The options for viewing the isolines can be changed by going to Draw Isolines, going to the Pour Water Pressure option, and then we see that we have selected the specific time step option here with the custom time steps where we've selected all of them from the window. If I want to also select all of the time steps, I can go to All, or I can select the option to display the current time step. The Draw Graph window is an excellent tool for interpreting and interrogating our model results. Go to the Draw Graph dialog, and then we can see that we have an existing plot for pour water pressure along the upstream face of our dam. In this case, we wish to view the graph such that y is on the y-axis. Right-click on the graph, select Options, and select the option Rotate 90 degrees. We now see that the y-axis has the y values on it. I can review the results from all time steps on the same plot by selecting All from the Select Time Steps option. In this case, we are viewing the results from our gradual drawdown analysis. We see that the pressure head gradually decreases from the initial hydrostatic conditions that were present at 0 seconds. If we click on 1A Rapid Drawdown, we will see that there is a much quicker shift in the pour water pressures or the pressure head over time after the initial conditions. Then the pressure head gradually decreases over time as pour water pressures within the dam dissipate. It is also important to check that convergence was reached for all time steps. I will do so by looking at a new plot, which I will call Convergence, and select the convergence type from the drop-down menu. Here we can consider the material properties plot, which shows the hydraulic conductivity over suction, comparing the inputted material property function with the computed one in blue. Or instead of selecting material properties, we can go to Convergence, Unconverged pressure head nodes over time. In this case, convergence was reached at all time steps because there are 0 unconverged pressure head nodes at each step. Now let us consider the results from the first slope stability case. Similar to the seepage results, we can click through the results times to view the critical subsurface and factor of safety determined for each time step. The lowest factor of safety occurs at the very first time step, following the initial conditions with their factor of safety of 0.982. In the Draw Graph window, a plot of factor of safety over time shows the immediate drop in factor of safety when the reservoir level instantaneously disappears. Click on the second slope stability case for gradual reservoir drawdown. We see a more gradual decline in the factor of safety, with the lowest factor of safety reached at 5 days when the reservoir has been completely removed. In this case, the factor of safety does not reach 1, confirming that gradual reservoir drawdown is preferred for maintaining dam stability. It is also important to consider convergence in slope W analyses. To do so, I will add a new graph and select the convergence type from the drop-down menu. This graph plots factor of safety over lambda. The graph includes 2 lines, one for the factor of safety based on the summation of the forces in blue, and one for the factor of safety based on summation of moments. These 2 lines have a clear intersection point that indicates good convergence has been reached. We can click through various slip surfaces near the critical value to make sure that a good intersection point is shown for all of these different slip surfaces. We want to do this for the slip surfaces in the other slope stability analysis as well to make sure that convergence was reached for both of the slope stability analyses. We have now finished reviewing this problem in GeoStudio. This example demonstrates the ease in which we can add multiple analyses into a project file and use results from one analysis in another. We saw that it was advantageous to use the Seep W pore water pressures for analyzing dam stability in slope W, particularly because we were able to investigate how the factor of safety changed over time, given the changing pore water pressures. I hope this webinar will assist you with future modeling endeavors. A recording of the webinar will be available to view online for the next week. Don't forget to look at the library of resources available on the GeoSlope website. And if you are unable to find what you are looking for, you can always send a message to our experienced team of support engineers by submitting a support request online. We have now reached the end of this webinar. Please take the time to complete the short survey that appears on your screen following the webinar so we know what types of webinars you are interested in attending in the future. Thank you very much for joining us and have a great rest of your day. Goodbye.